So we are going to start our lecture or series of lectures today with beam bending, buckling, and torsion in this series of lectures. So we are going to look at bending, we're going to look at buckling, and torsion respectively. So hopefully you've seen beam bending in other courses, and obviously there are quite a few courses where, civil engineering, structural applications, but there's also more exotic basically applications of beam bending with atomic force microscopy, honeycomb structures, cellular structures, and so many applications of beam bending. So I think that there's little to no motivation that we have to do for this topic. But we want to go over some basics. So when you're dealing with beam bending, we're going to look at support reactions, forces, internal forces, stresses. We're going to look at different supports, rollers, pins, etc., fixed supports. So there's going to be some basics of beam bending that you want to review. You've seen this hopefully in statics and other courses, fixed supports, and we're going to look at this in the context of, are there reaction forces? Are there reaction moments? What are the boundary conditions when we're solving our fourth order ODE to figure out beam deflection, to find out maximum shear forces, to find out maximum bending moments, to find out maximum stresses, internal stresses in our beam. So they're all going to be critically important. So one of the things, sign conventions, coordinate systems, just again, another reminder. So we're going to look at and define negative shear forces, and we're going to define tension. Again, it's going to be positive. Compression is going to be negative. Shear forces, they're going to be positive if they're acting on a face with a normal positive in the direction. So we've seen those before. But there are a couple of kind of unique definitions for beam bending. So moments, counterclockwise positive, clockwise negative. If we are looking at a cut on the right-hand side, if we have a positive shear force, it is going to point down, and the opposite one on the other face is going to point up there. Moments, as you see here, if it's bending upwards, positive curvature, positive moment. Negative curvature, negative moment. Same thing here, you can see here the shear forces, again, what I was saying, the negative there, if it's on the, again, that right-hand side, if it's pointing up, then that's a negative shear moment. So remember, for curvature or for bending moment, and you can see here, positive is acting downward on that right-hand face, negative if it's acting upwards. Moment, if we have tension on the bottom of our beam, that's a positive bending moment. If we have tension at the top of our beam, that is going to be a negative moment. So hopefully you've seen basically all of these different types of definitions, but this is the nomenclature. This is how we're going to define positive and negative in this course. So if you're doing a different coordinate system, make sure that you specify that when you're working on problems. So let's kind of review some quick support reactions in beams. So let's first consider, again, a cantilever beam, length L, load applied at the end. So we have a fixed end, and we're going to have a reaction force in another direction. And whenever we're solving these problems, we need to define our coordinate system, draw a free-body diagram, equilibrium expressions, and solve for our unknowns. So what are our equilibrium conditions? Static equilibrium, some of the forces, some of the moments must be equal to one another. So we can see here on that cantilever beam, I apply a load at the end. If it's a fixed support, I'm going to have reaction moment in the Y, or a reaction force in the Y. I'm going to have a reaction moment as well that opposes essentially the moment that's being applied on that beam. And I can basically, again, define my coordinate system. I drew my free body diagram. I could develop my equilibrium equations, as you see there, and then solve for my unknowns. Specifically, that reaction force in the Y is equal to P, and my reaction moment essentially at the end of that beam at a basically x value of 0 is going to be PL. So we have that for our first kind of beam bending problem. You can do the same thing for a distributed load type problem. So there's a distributed load there plus an additional force being applied. Same thing, coordinate system, free body diagrams. We have our equilibrium expressions, and then solve for your unknowns. So these are kind of the basics. These are assumed knowledge in this course. You've seen this in statics. This should be all review, but it's going to be important once we start to get into more complex beam deflections and then trying to solve for beam stress values as well. So those are the basics, and we'll see you next time.